Once again, I would like to thank the organizers for giving me this opportunity, a rare opportunity indeed, to present my work. This work is a working paper. I'm doing it with my colleague, Dr. Farah Mshama, and the idea emanated from Professor Ben in Oslo. The structure of the talk, I'm going to do the motivational study about it and review the difference between contract quantum formula, and then present the asset dynamics under the HJM framework, and the primer on the Malliavin calculus, and then do the sensitivity analysis on it, and then conclude. Muller and Granti, around 2000, put forward the following citation by a famous American writer, philosopher, was everything Mark Twain. Everybody talks about the weather, but nobody does anything about it. This was around 100 years ago, late 1800s and early 1900s. In 2007, Carmona, in one of his lectures, put forward this citation. Weather is not just an environmental issue. It is a major economic factor. At least $1 trillion of our economy is weather sensitive. This was said by William Dell in 1998. He is the U.S. Commerce Secretary. Furthermore, he said that 20% of the world economy is estimated to be affected by weather. Around that time, we are talking of some 20 years ago now. The weather hedge idea has taken root, particularly in commodity and energy sector, where instruments for hedging weather risk are now common. Energy quantum derivatives are part and parcel of the exotic group of options which take advantage of correlation between energy, commodity price, and state of the weather. And this can be elaborated further in Kaporin in this paper 2012. The general comparison of the currency quantum option and regular core put off versus the energy quantum option is in the structure of how these are written. The first one, the currency quantum option, has got a structure of the classical payoff where you got a process and a strike. But this one, the energy quantum option, you will have a product, one emanating from the price of the energy bill, and the other one emanating from the weather. So it becomes a product. That's how they differ from the normal quantum option. So the energy quantum option gives exposure to joint price and volume risk. Okay, this is going to be explained in the coming slide. Belt and Lunch in 2012, among those who pioneered this hedging debate. In fact, Professor Belt was supervising Lunch in 2012, and I visited them, and that's where the debate of this topic came from. I looked around here, locally, what is happening with this. I realized that in South Africa, the quantum commodity derivatives are structured differently, but they are happening. At the bottom here, you can see that the Rand Merchant Bank played a pioneering role in bringing this product to the market in 2012. So you can actually visit this website and see in detail what is happening here. But if you read some of the documents, according to the JSC, a quantum commodity futures or option can be understood as follows. If the price of a commodity, say Brent crude, increased by 20% in dollar terms, then the value of the investor rand position in Brent crude via quantum product will also increase by 20%. The movement of the rand relative to the dollar has no part in determining this investment. If you look at it closely, you realize that it doesn't differ with the standard product. What they only doing is hedging the exchange rate risk there. But they got metals like oil, commodities, even gold. These products are available, but they are structured differently. Right, the energy market, which is structured. These are a few examples. You can get the New York Mercantile Exchange, Chicago, and the German Exchange as well. We mentioned the typical energy market as described in 2015, which constitutes the following: that we got to the spot auction-based day-ahead spot market of hourly delivery of the energy, and the futures delivery energy over weeks, months, quarters, and years ahead. Year delivery is the average spot of the delivery period. For instance, here you can actually see that the energy is represented by the average of the spot over the term of delivery from tower 1 to tower 2, where SU is an energy spot price. The weather market, which brings the other component, for instance, Chicago Mercantile Exchange trades weather derivatives. There are quite a range of them. Among them, we can see hurricanes, snow, rainfall, temperature, etc. But in this talk, I'm going to present the temperature type of weather derivative. Options, futures are written on monthly seasonal temperature indices. For instance, the US, Asia, European cities, and not of what I know in Africa. I'm not sure whether it is there as yet. In Japan, they have also introduced the Clark-Ocone indices are the heating degree days, HDD, and the accumulative degrees when temperature T is below. In America, in Europe, and Asia, they are using 18 degrees as the strike, and cooling degree days, the accumulated degrees when temperature is above. So, I will represent the I index here as the summation of the temperature reading. The term U, and G is some function. For instance, G can represent this structure here, which looks like a European call option, where this will be the price process and 18 strike. Plus means anything x minus 18 and 0, any of the two being the maximum. So we consider a positive value there if an HDD temperature index is considered. Right, now I go on to the modeling framework. We consider a probability space where we got the universal set, the sigma algebra. These are filtration or subsets of what emanates from the universal set, and with some filtration, and this filtration with some measure. Filtration will be modeling information known up to a certain time. And the Brownian motion here, we're going to call it the Wiener space, W. We are going to put a structure to this omega apart from the norm, which is normally a family of continuous functions. so that the Malliavin different will accept Malliavin differentiability, so that we can the usual Malliavin calculus. Actually, this phenomenon of Malliavin calculus is a sort of non-standard, and when you differentiate, we are differentiating in a different, sometimes different, also coincide with the classical way of doing it. Right, now the quantum pricing. What you're going to see here is that we're going to follow a quantum option whose payoff is constituting of two items: E, which is the energy index or commodity index, and I, the temperature. So considering a period tau 1 to tau 2 where tau 1 is less than tau 2, the quantum option therefore can be considered to be the following: T equal to E up T here, and then this little T here is representing filtration of this whole process up to time T, and Q is the pricing measure, and F can represent either a different type of payoff you will consider. Here, R is positive and represent the constant risk-free interest rate. If we price quantum option on futures on energy and temperature index E and I in a delivery period T1, tau 1, tau 2, we will have it. This is the forward or the futures E equal to the expectation of the average. So this index here E is representing the energy, and we are going to do it up to the final period tau 2, and this is the relationship we will get. So applying the same argument for temperature, we are going to see that our structure of our option will be like this. Now this one is Fi. So everything else I've explained it before, and you can see now that the payoff of this K bar I, the strike of the temperature at 18 degrees, AE, strike of the energy process, and some are for call and some for the puts. So you can write the whole payoff with alpha, which is the notional volume index, and maximum of this and that plus that of the call option. As you can see, this is quite long, and for the purpose of illustration, we're going to summarize this expression, possibly ignoring the other put side of the story. I'll work with this first component. So it will be looking like this. The quantum option at time T will be given by this price process. Now you would have seen that taken a layer. It is difficult because of the liquidity in the market to price using the underlying asset. Then we move on to the layer of futures. The futures market normally there's liquidity, so some of procedures will work well. How to hedge the quantum products, the Greeks. Now, if you analyze this paper by Ben, he has partly done what I'm going to talk about, but there's a difference. The difference is around this question of regularity issue. What they've done is possible with many type of not many, but some payoff functions like the European type. But if you are to deal with a payoff which is discontinuous, like a quantum payoff, a digital payoff, then you will find that will be a problem. The framework which I'm going to operate will be the Heath-Jarrow-Merton method, actually not Merton, but Morton framework, emanated around 1980 to 1987. They put this framework of model to deal with bond and interest rate. So, because the behavior of energy and commodities, they just rhyme with that of interest rate. Therefore, we have adopted this into the modeling of energy options. Sorry. Right. So explicitly, you get such an expression, and all these should make sense in the sense that these integrable conditions should be satisfied. And normally, under the AJM framework, the volatility is taken to be this expression here, sigma I, which I have represented here, will represent energy and temperature. Right, so the payoff, as I've alluded to, will have a G payoff representing energy and H representing the weather, the temperature. And these conditions are fulfilled. Because we're going to do a special differentiability of Malliavin calculus techniques, this is a little bit abstract in some sense. It happens in L2. Strictly speaking, Malliavin derivatives are infinite type of differential operators. So for it to be usable in practical sense, we need some conditions for it to be closable. And then so this theoretical aspect is done in a general way. I could have put it in an appendix, but for instance, if you got a random variable here, f, capital letter F represented by all this, where f is infinitely differentiable function, what you will see is that we differentiate, it becomes a partial derivative of this partial derivative with respect to xi, and then this is left like this, but then times the argument. You get inside the argument, and then you start the differentiating. And then there are properties. You see, the property of plausible, when you are going to an infinite dimensional operator, you need to differentiate. You need to make sure that it is plausible operator. And these norms are got a domain with respect to this norm. So remember, f is the function f alluded to. And you're dealing with the norm space, which is a balance space. And the Malliavin derivative is an adjoint operator called the square code, because you need an adjoint operator when you want to swap things which are of infinite dimensional nature. And there is another property here where we've got a stochastic process U in the action, and U is also an element of the domain of the square code operator. We have that. Operator. Right, okay, we'll continue. This comfort integral is coincides with the hydro integral, where the delta U is integral of this. And then we've got this other property where the sort of operator appearing like this. Looks like integration by parts. Right. So if one wants to look in detail those properties, there are these references which I've alluded to. Nuala is one of them. And in 1991, Clark and his supervisor, Caracas, in 1991, they were studying some hedging of call options in a complete market. So what you see here is the what you so-called the Clark-Ocone Representation. It looks like a martingale representation, but the difference that now this integrand here has a Malliavin derivative type. This integrand. So this integrand here coincides with what exactly we do when we are calculating the Greeks and sensitivity in risk analysis of options. Our main task is to calculate this integrand. Right. So we structure this in two cases. The independent case. Suppose the weather is independent to the energy. As a base or benchmark value we were able to get. Next, what we then did was to look when they are correlated. So,
what do you mean the weather is independent of energy? Sorry.
Well, it is hypothetical that I want to make it independent. Huh? Like that, it's indifferent what the weather energy price process doing in different
energy price, not energy.
Yes. Or then consider when there's real correlation. In fact, the quantum came as a result of this correlation. That what happens with the weather, with your cooling system when it is hot, you have to hedge against the volume of the quantities you are expecting and do that. So here, look, this delta here is representing the delta of the energy with respect to the future. Partial of the call option with respect to the energy. Then do the same with respect to temperature. But what you are seeing here is that you don't see any, this is the result, you don't see any differentiability except this term which actually has been found in literature to be listed. For instance, AT to 1 over T. This AT is actually summing to 1. It's sort of like a gauge ratio of stochastic flow. Right. Here I gave an idea of how to maneuver this. So what I'll do is to introduce this E, this expression, say representing 1. This implies that you can summarize the exponential part like this. Using the Malliavin calculus, of which I'm not going to explain, you see some of the characteristic equation appearing here. And so you multiply both sides doing the derivation. This is only the sketch of the proof, and what you obtain finally will be the expression I've shown you. Do the same with the temperature, and we propose and so that this is what you. And also, because we've got a product, we have to do what we call a cross hedge. Cross hedge, that how the other is doing with respect to the other quantity. So the procedure is not different, but what you see now, you've got these two Malliavin weights which are appearing here. What I can say is that this These expressions are very now suitable for application of Monte Carlo. This G is to be specified, and this H is to be specified. Now, you don't lose sleep to say, well, how about if G is a discontinuous function? Because otherwise, you only restrict yourself to apply the Logan option. But if G is discontinuous, because of the power of the Malliavin derivative, we manage to get the expression. And whatever get is there is ironed by this quantity here. And right, this is the correlation case. I will explain the first part, how we sort of correlate this. So we suppose these two Brownian motions for B1 and B2, which are independent, and we fix that W1 is equal to B1 and W equals to 2. So this is rho, which is the correlation coefficient, and then the product will then appear this way. This is different from the previous case because we didn't have a rho there, and now that's being reversed. The payoff, which is version 9, the Quanto option structure is going to be like this. So this is a little bit longer expression. What are we going to do with this one? We're going to differentiate with respect to the energy, and then do it again with respect to the temperature futures. This is precisely what everyone does when we are dealing with the bricks. And then correlation test, when you do apply the properties of Malliavin calculus, you are going to get the expressions like this. And then this is your energy, your Malliavin weight. Right. At this stage, what we have been calculating actually are what is currently known in literature as dirty hedge. You can appreciate that dirty hedges are hedges which you can't completely hedge. So they are nicknamed dirty hedges. So what is the resultant? The resultant is that there is always going to be a residual risk. So the idea which I had earlier was to say, let the two processes be independent, and then let it be correlated. Then this difference between the two values will precisely give us what we call the residuals. So, in conclusion, what we have reviewed here are the commodity quantum options. We have provided derivative-free for the deltas and cross gamma for the product via Malliavin calculus, which are ready for Monte Carlo application. We also gave a remark on this residual risk. What remains to be done in the next paper are the numerical experiment to ascertain the effectiveness of the proposed formula. And these are some of the references which I have utilized. I conclude. Thank you very much.